from a square matrix is known as determinant of a matrix. The determinant of a matrix A is denoted as A mod or determinant of A. The determinant of a 1 by 1 matrix. Determinant of a 1 by 1 matrix is the number itself in the matrix. For example, we have the matrix A is equal to 9, which is 1 by 1 matrix. So the determinant of the matrix A is A mod is equal to 9, number given in the matrix itself. The determinant of a 2 by 2 matrix. The determinant of a matrix which is 2 by 2 is found by subtracting the product of its diagonals. That is, the matrix A is given by A11, A12, A21, A22, then A determinant is equal to A11 multiplied by A22 minus A12 multiplied by A21. Find the determinant of a matrix A which is given by 4, 1, 3, 2. The determinant of the given matrix is A determinant is equal to 4 multiplied by 3 minus 1 multiplied by 2, that is determinant of A is equal to 10. The determinant of a 3 by 3 matrix. The determinant of a matrix A which is 3 by 3 can be found by the following procedure. Number 1, write the first two columns of the matrix to the right of the original matrix. Number 2, multiply the down diagonals and add them together. Number 3, multiply the up diagonals and add them together. Number 4, the determinant equals to the sum of the products of down diagonals minus the sum of products of up diagonals. The determinant of a 3 by 3 matrix. Algebraically, the determinant is computed as A determinant is equal to the product of red lines, the first red line A11 multiplied by A22 multiplied by A33 plus A12 multiplied by A23 multiplied by A31 plus A13 multiplied by A21 multiplied by A32 minus the other three green lines. Find the determinant of a matrix A which is given here. To find the determinant of the matrix A, firstly we will write the first two columns of the matrix A at the right side of the matrix. That is, A is equal to matrix A and the first two columns, and then we see the three red lines and three green lines. Now the determinant is computed as A determinant is equal to the product of red lines minus the product of green lines, which is given by A determinant is equal to 103. The method of cofactors. The method of cofactors is the most generalized computational procedure which can be applied for all square matrices. Following are the steps to find the cofactors. Number 1, firstly we have to cross off row I and column J in the original matrix. Number 2, focus on the remaining terms of the matrix. The remaining terms of the matrix form a submatrix of the original matrix. Number 3, find the determinant of the remaining matrix known as minor of the element Aij. Number 4, the factor Aij prime is found by multiplying the minor by either +1 or -1 depending on the position of the element Aij. The method of cofactors. Formula for computing cofactors is Aij prime is equal to -1 power I plus j times the minor. Method of cofactor expansion. Select any row or column of the matrix, multiply each element in the row or column by its corresponding cofactor and sum these products to yield the determinants. The determinant of a m by m matrix A can be calculated using the method of cofactors expansion. That is, A determinant is equal to AI1 prime plus AI2 prime plus and so on up till AIM prime. Example, find the determinant of a matrix A which is given by. The determinant of the given matrix can be found by the method of cofactor expansion. That is, determinant of A is equal to AI1 prime and up till so on So we get A is equal to crossing the first row and first column. By the formula, the cofactor is computed as A11 prime is equal to minus 1 power 1 plus 1 times minus 2587, that is equal to minus 54. Similarly, writing A again and selecting the first row and second column, so we get A21 prime is equal to minus 1 power 1 plus 2 times 4527, which is equal to minus 18. Again, writing the matrix A and selecting the first row and third column, we get A31 prime is equal to minus 1 power 1 plus 3, and we get 36. Now we will substitute these cofactors in the cofactor expansion, that is determinant of A is equal to A11 prime plus A21 prime plus A31 prime. Now putting all the values, determinant of A is equal to minus 306. Dear students, now we see some properties of determinants. Number 1, if all elements of any row or column equal to 0, then the determinant of that matrix is equal to 0. Number 2, if any two rows or columns are interchanged, then the sign of the determinant changes. Number 3, if the matrix B is obtained from the matrix A by multiplying each element of the matrix A by a scalar k, then we get A determinant is equal to k times B determinant. Number 4, if any multiple of one row or column is added to another row or column, the value of the determinant is unchanged. Number 5, if two rows or columns are identical, then the determinant is 0. Dear students, now we see another method to solve the system of equations. This is called Cramer's rule. Given a system of linear equations of the form Ax is equal to b, where A is n by n square matrix of coefficients, Cramer's rules provides us a method to solve the system of equations by using the determinants. To solve for the value of jth variable from matrix A, J, replacing the jth column of A with the column vector of B. The value of jth variable is determined as xj is equal to aj determinant divided by A determinant. Example: total 820 tickets were sold for a game for a total of $9,128. If adult tickets were sold for $12 and children tickets were sold for $8, how many of each kind of tickets were sold? Let x be the number of adult tickets and y be the number of children tickets. Then we have the system of two linear equations in two unknowns. The first linear equation is given by x plus y is equal to 820, and the second linear equation is given by 12x plus 8y is equal to 9128. Now we apply the Cramer's rule to solve the system Ax is equal to b. The matrix A is given by 1, 1, 12, 8. The matrix X is xy, and the matrix B is 820 and 9128. So first of all, we find the determinant of A, which is given by 8 multiplied by 1 minus 1 multiplied by 12, that is A determinant is equal to minus 4. Now interchange the first column of matrix A by the column of matrix B. So A1 is equal to 820, 9128. First column is interchanged and the second column is itself 1, 8. So therefore determinant of A1 is equal to minus 2568. Now x is calculated by dividing the determinant of A1 by the determinant of A. That is, x is equal to minus 2568 divided by minus 4. So we get x is equal to 642. Now interchange the second column of matrix A by the column of matrix B. That is, we get A2 is equal to 112, which was the first column, and the second column is interchanged and it becomes 820 and 9128. So A2 determinant is equal to minus 712. And similarly, we get y is equal to determinant of A2 divided by determinant of A, that is y is equal to minus 712 divided by minus 4, that is y is equal to 178. So we have 642 adult tickets and 178 children tickets. Dear students, now we see another example. The equilibrium conditions for the two related markets are given below, where PC is the price of chicken and PB is the price of beef. The first linear equation is 18 PB minus PC is equal to 87, and the second linear equation is minus 2 PB plus 36 PC is equal to 98. So we have to find the equilibrium price of each market, PC and PB. The following system of linear equations represent it in the matrix form AX is equal to B, where the matrix A is given by here, the matrix X is PB and PC, and the matrix B is given on the right side. Now, applying the Cramer's rule to solve the system, first of all, we have A is equal to given by, then we calculate the determinant of A, which is 646. Now interchange the first column of matrix A by the column of matrix B, so we get A1 matrix, which is given by here. Then we calculate the determinant of A1, which is 3230. Now we calculate the PB, that is dividing the determinant of A1 by the determinant of A. So we get 3230 divided by 646. Therefore, PB is equal to 5. Now interchange the second column of the matrix A by the column of matrix B. So we get A2 is equal to given by. Now we calculate the determinant of A2, which is given by 1938. And again we get PC is equal to A2 determinant divided by A determinant, which is given by 1938 divided by 646. So PC is equal to 3. So we can interpret these results that the equilibrium price for each market is PC is 3 and PB is 5. The inverse of a matrix. The inverse of any matrix A is denoted by A power minus 1 with the property that A multiplied by A inverse is equal to A inverse multiplied by A is equal to I, which is the identity matrix. Note that A inverse doesn't mean that we have 1 divided by A. Important points regarding the inverse. Number 1, for a matrix A to have an inverse, it must be a square matrix. Number 2, inverse of a matrix A will also be square and of the same dimension as A. Number 3, not every square matrix has an inverse. The inverse of a matrix. Determining the inverse. There are several methods for determining the inverse of a matrix. One of them is Gaussian elimination procedure, and it is also called Gaussian reduction procedure. To determine the inverse of a M by M matrix A, we have the following steps. Number 1, augment the matrix A with the M by M identity matrix, resulting in A augmented by matrix I. Number 2, perform row operations on the entire augmented matrix so that to transform A into a M by M identity matrix. Then the matrix will have the following form: A augmented by A inverse, where A inverse can be read to the right of the vertical line. Example, let's determine the inverse of the matrix A, which is given by 1, 2, 3, 4. Use the Gauss elimination method to transform A augmented by I into A augmented by A inverse. We will do some row operations to make the matrix A into identity matrix. As a result, the changes occur in the identity matrix will give us the inverse of matrix A. So we write A augmented by I. Then we do some row operations. For example, in the first step, we multiply the row 1 by minus 3 and add it to row 2. In the second step, we multiply the row 2 by minus 1 over 2. And in the third step, we multiply the row 2 to minus 2 and add it to the first row. So the first matrix changes into the identity matrix, that is 1, 0, 0, 1. And the identity matrix changes into the A inverse, which is given by -2, 1, 3 by 2, -1 by 2. Finding the inverse using the cofactors. Dear students, this is another method to find the inverse. The cofactor method for finding the inverse of the square matrix A is as follows. Number 1, determine the matrix of cofactors AC for the matrix A. Number 2, determine the adjoint matrix AJ, which is transpose of the matrix AC. Number 3, the inverse of matrix A can be found by dividing the determinant of the matrix A with the adjoint matrix. That is, A inverse is equal to 1 over A determinant multiplied by adjoint of A. The inverse and system of equations. The matrix inverse can be used to determine the solution set for a system of equations. Given a system of equations of the form Ax is equal to B, where A is a square matrix, if we multiply both sides with inverse of a matrix A, then we have x is equal to A inverse multiplied by B. That is the solution vector for the system of equations. Example: the input-output matrix for a 3-industry economy is given by, on the right side we have suppliers 1, 2, 3, on the top we have users 1, 2, 3, and it is given in the matrix form by A. If the non-industrial demands are respectively these amounts, then we have to determine the equilibrium level of output for the 3 industries. The non-industry demands are given in the matrix D. The equilibrium level of the output matrix can be determined by using the formula I minus A inverse times D is equal to X. So I is the identity matrix. First of all, we calculate I minus A, which is given by identity matrix minus A matrix. We do the corresponding subtraction and we get I minus A. Then we take the I minus A inverse using the augmented matrix. So now we calculate I minus A inverse using the augmented matrix. We do some row operations one by one. In the first step, we divide R1 by 0.75. In the second step, we take R2 and add it to 0.20 times R1. In the third step, we add R3 and 0.40 times R1. And in the fourth step, we divide R2 by 0.62. And in the last step, we add R3 and 0.6 times R2, and R1 is added to 0.399 R2. We divide R3 by 0.537 and we do the further row operations, so we get the I minus A inverse matrix. Now we multiply I minus A inverse by the non-industry demand matrix D, so we get the following matrix. And this is called technology matrix or input-output matrix. Here Aij represents the amount of industry I's output required in producing $1 of output in industry J. For example, the element A11 is equal to 0.25 suggests that every dollar of output from industry 1, 25% of this value is contributed by industry 1. The element A12 is equal to 0.30 indicates that for every dollar of output from industry 2, 30% is contributed by industry 1. The element A13 is equal to 0.20 indicates that for every dollar of output from industry 3 requires 20% of output from industry 1 and so on. Hence, industry 1 should produce 1988000,000 worth of output. Industry 2 should produce 32186,000,000 worth of output, and industry 3 should produce 44605,000,000 worth of output in order to bring supply